Okay, good morning, everybody. So the plan today is to just continue on with chapter 6 with normal distributions. We should finish up the standard normal distribution discussion and get started on general normal distributions today. The quote of the day today is one related to, I think, research and science and really almost any field of inquiry, that the outcome of any serious research can only be to make two questions grow where only one grew before. So if we're doing research into a topic and kind of ending up with fewer and fewer answers and, in some sense being more and more conceited in our knowledge, maybe we're not taking that research actually as seriously as we ought to. When we're doing more research, we're answering questions, of course, but that naturally leads to even more questions and hopefully keeps us from being too conceited in our knowledge, thinking that we uh, are on the approach to knowing everything, right? Whenever we answer one question and don't care to ask any more, then we're confident that we know everything. When we answer one question and then three more pop up, and we answer one of those and three more pop up, like a hydra or something, then maybe we realize how much there is actually to explore out there. And just one more plug for a new philosophy course being offered in the fall, Philosophy 206, Philosophy of Science. It is available on the catalog right now. I think registration starts in about a week or so for fall. So I mentioned this one before. It's being taught by our philosophy professor Drew Van Land at Allegheny, and the details are available now. It's a 3-credit course. There are no prereqs, so you don't have to have any philosophy like 101 or anything like that. You can just sign up for this course if you're interested. It is located on campus at Allegheny campus Monday, Wednesday, 12 to 1:15. So I know that if you're taking the remote modality, there might be attending a lecture like that might be a challenge, but if you have that availability in your schedule, and honestly, if I was taking a philosophy course where you want to have kind of more active discussion and so on, that actually might work better in an in-person environment than remote. People, for whatever reason, tend to interact differently in remote settings than when they're actually face to face. And I think this may be, this is just the blurb from the catalog, but I think this section kind of sums it up pretty well. Students will study the practice using the abstract insights of philosophy to both learn scientific subject matter more effectively and to critically analyze scientific claims. So I think even if you're not planning to be a scientist, just this idea, right? I mean, science is pervasive these days. People are making claims, and usually our question is, well, what's the evidence in support of your claim? And by that, we're asking essentially a scientific type of question. We're typically not expecting them to present their evidence in the form of, say, a mathematical proof or in terms of, say, their credibility or something like that. We're often asking them, well, can you show me an experiment or some scientific rationale for your that supports your claim? So anyway, I think it's an interesting course. First time it's being offered this fall, and those are the details. Okay, so let's jump down to normal distributions again. The normal table is on Blackboard. I posted in a chat last time. So it would definitely be helpful if you have this PDF table or one printed out, open and available to you. I know the numbers are pretty small on my screen, so I'm kind of counting on you having one in front of you that you can kind of follow along at a more manageable size. And let's just remember how all of this works from last time. We remember that, we get a little more space here. We remember that when we say Z, that's kind of a trademarked variable in probability and statistics, meaning the standard normal distribution, that is the normal distribution with a mean of 0 and a standard deviation of 1. Now, the normal distribution, its parameters are often reported as the mean and the variance, but I'm reporting them as the mean and the standard deviation, just for clarity. And we know that our normal distribution is our so-called bell-shaped curve. The peak is at the mean. In this case, when we're looking at z, it's at 0. And we said that the standard deviation, that these inflection points where we go from being concave up to down or vice versa, these are one standard deviation away from the mean. So these are at +1 and -1. And we can ask a question like, what's the probability z is less than -0.398, for instance? So I draw my picture. I think it's always worthwhile to draw a picture. There's 0. I see I'm interested in a z index, a location on the horizontal axis of about -0.4 or so. So maybe I'll note my inflection point down here at -1. And I see -0.398 will be somewhere in there. I'm asking for the probability z is less than that. So I'm looking for the area to the left of that line under the curve. And I see that this area, well, if this area went all the way up to 0, it would be 50%. It's missing a little bit of that area. So it's going to be less than 50%. But I also just kind of intuitively see it shouldn't be a whole lot less. It shouldn't be like 5%, maybe like 40%, maybe like 35%, maybe like 45%, something like that, maybe. Certainly should not be above 50%, but it also shouldn't be a tiny area. And here we'll jump over to our normal table. Let me actually resize this window just a little bit so that I can try to get both of these on the screen at the same time. There we go. Oh, need a little more. Okay. Everything in Microsoft these days wants to just clutter up all of the open space they have. There's all of these things on the right-hand side, and I don't know. I feel like Microsoft is slowly taking all of the little pieces of area that used to just be kind of clean and there wasn't anything there and cluttering it up with all kind of stuff to try to sell you more features. Okay, so we're looking for the side of the table that matches this picture better. Well, that's not the positive z-score side. That would be the negative z-score side. That's also the side associated with negative z indices. And that's also the side associated with probabilities, areas in the middle here, of less than 50%. So this is probably the side of the table we should be on. That matches all of those 3 criteria. And I'm looking for the area to the left of what? Well, -0.398. Well, my table allows me to index down to the 10th place and then the 100th place, but not the 1000th place. So the first thing I'll do is I'll say, well, this is approximately probability z less than -0 point, and I want to round this to the 100th place, to the second decimal place. But the 8 makes the 9 round up, but the 9 rounds up to a 10, making it 0.40. So I'm looking for probability z less than -0.40. So I see, looking down my index column here, going down to -0.4, that indicates this row. So my the area that I'm looking for is going to be somewhere in this row, the -0.4 row. And then I want 0/100ths, which means it's going to be in the leftmost column of the field of the table. And the intersection of that row and that column is this number, 0.3446. Or 34.446%. That does mesh with my initial expectation, area less than 50%, so I think I'm happy with that. Let's also look at how to find these normal probabilities in Excel. We're not going to do too much work in Excel on these. but just to show you how to find them. So my Z index that I'm interested in is negative 0.398. So if I'm looking for the probability Z less than negative 0.398, I'll jump over to the C column for this, I guess, just so I'm not overlapping my uh, my text that I typed in there. And here I'll do equals because I want Excel to compute something. NORM is kind of the normal distribution reference. And we see we have a couple of different options here. Norm.dist returns the normal distribution for specified mean and standard deviation. Norm.inverse returns the inverse of the distribution. So the inverse would be like if I give you a probability and I want the index, but norm.dist is the one that we want. The x, or the index, the horizontal axis index that we are referring to is this negative 0.398. We're on the standard normal, so the mean is 0. The standard deviation is 1. And cumulative, if I write false, I'm kind of asking for a PDF for just the height of the PDF there. But I want true. I want the whole area to the left. So Excel is also kind of implicitly set up to give areas to the left. And I see this 0.34532. That's pretty close to 0.3446. There's a little bit of rounding here. If I made this negative 0.4 instead, we'd see exactly our 0.3446 once we round it to 4 decimal places. But Excel can actually be a little more accurate than our table. It can take this negative 0.398 and get the answer for that even down to the thousandths place. So it gives a little more accurate of an answer. So the answers you get on Excel are sometimes a little bit off of what you would get from the table. And that could be due to the fact that the table is rounded to 4 decimal places. And it could also be due to the fact that we're often rounding our Z-score, our Z-index, to the hundredths place, because that's the level of accuracy of the table. But in Excel, just our norm.dist function, normal.distribution, gives us the probability as well. Okay, and let's come back and look at probability Z bigger than -1. We looked at this a little bit last time. We mentioned that there were 2 ways to approach this problem. The big issue with this problem is we have an area to the right. So here is -1. And I'm looking for the area to the right of -1. Now I know this should be bigger than 50%. It should be a decent bit bigger than 50%, not like 51% or something, but it also shouldn't be like 99%. So my problem is that I have an area to the right, but my table gives me areas to the left. And note that, it's not just this table. Excel also gives me areas to the left. So, right, we have to get used to being able to convert, areas on one side, areas on the other side, to be able to move around confidently between these different areas. So we have 2 methods. The one we discussed last time was using complements. So I can take the area to the right of -1, and I could rewrite this area, or kind of reinterpret this area as being the whole area under the curve, including this left tail. So that includes the area that I want. Here's -1. That's the area that I want to keep, but it also includes a bunch of area that I don't want to keep. So to recover my original area, I just need to get rid of the area to the left of -1. So if I take the whole area under the distribution and subtract off the area to the left of -1, that leaves me with just the area to the right of -1. And then if I rephrase that in terms of probabilities, probability z is bigger than -1 equals, well, the total area under the distribution by rule has to be 1. That was one of the criteria to be a PDF, and the normal distribution function certainly is a PDF. And then minus probability that z is less than -1. So thinking of it graphically like this, we could also think of it just with the complementary event rules that z bigger than -1 and z less than -1 are complementary events in the context of continuous distributions where probability z equals -1 is 0. Make sure that if you're dealing with a discrete distribution, if you're working on, a homework or an exam problem or something on chapter 5, then that less than versus less than or equal to is a very important difference, but not in continuous distributions. Now, probability z less than -1, I can find that on my table. I'm looking for the area to the left of -1.0 and 0/100ths. So that is 0.1587. Now, again, like I mentioned last time, it can be a little bit tempting to see that 0.1587. We did a bunch of work and feel like that's the answer and put that in. But remember, that actually goes here. And even if we were tempted to think that 0.1587 was the answer, we check against our original estimate for the answer. The original estimate's bigger than 50%. 0.1587 is less than 50%. Something's gone wrong. But we can see that when we do 1 minus 0.1587, that gives us 0.8413, 84.13%. And that looks like what we were expecting, something that is a decent bit bigger than 50%, but not really close to 100%. So I'm pretty confident in that answer. There's a second method that we could use. So to be clear, at this point, we've completed the problem. We can enter this answer into MyStatLab, hit submit, and we'd be done. But it's always nice to have more than one tool in your toolbox, right? If I want to put a nail in, it's nice to have a hammer. If I want to put a screw in, I'd like to have a screwdriver as well as a hammer. So it's nice to have knowledge of both of these methods. You can probably get away with just using complements, in almost all cases, I think. But using symmetry just comes in so handy so much of the time. It avoids, in some problems, it avoids so much complexity with the algebra and all of that kind of stuff. So I would recommend learning both. So the second approach is to make use of the symmetry of the normal distribution. So here's z, there's 0. And again, remember, we're looking for probability z bigger than -1. Same problem. So we're looking for this area, which we know is bigger than 50%. Now, instead of using complementary event, there's another way that I could turn this right tail into a left tail area. I could make use of the fact that z is symmetric about 0, and I could actually flip the whole picture over 0. If I do that, the black curve looks the same because it's symmetric about 0. If I flip over 0, my -1 index just becomes its opposite. It becomes a +1 index. So it's +1 now. I write it as +1, but normally just write it as 1. And my area to the right, like kind of this chunk of area here, flips over and becomes this chunk here. And this original tail to the right flips over and becomes this tail to the left. So my area that I'm looking for now is this one. The area to the left of +1. So probability z bigger than -1 equals, by symmetry, probability z, this is still z, probability z less than +1. Be really careful that you don't get the two conflated, that you don't, grab onto like part of the complementary method and part of the symmetry method, right? The complementary method, probability z bigger than -1, is 1 minus probability z less than -1. The index stays the same. We're keeping the same index the whole time. We're just kind of shifting which side the area is on. For symmetry, the index actually changes, right? So in one of them, the inequality sign changes, but the sign plus or minus of the index does not change. For the other one, the inequality changes and the plus minus changes. This is why I think it's good to write out the pictures. It can be easy to just make a little algebra flub, a little mess up with a negative or something like that, and get a wrong answer. But I see that probability z less than 1. I can look that up on the table. I'm looking for really this picture here. So that doesn't mesh with the negative z-score side of the table, but it meshes with the positive z-score side of the table. 1 is a positive number. This picture looks more like the picture over here. And my areas are bigger than 50%. So probability z less than +1. So I'm looking for 1.0, that row, and 0 hundredths. The intersection of that row and column is 0.8413. And we get exactly the same answer we got before. So if you were on an exam or something, do not do it both ways. Don't spend the extra time on an exam or when there's a time crunch to do it both ways. But if you're, working back through the notes, you might look at maybe this example we do via symmetry. Maybe as you're rewriting your notes or looking back over them, you say, hey, can I do that one with complements? See if you get the same answer, or vice versa. Maybe we do this one with using complementary events. Say, hey, can I do that one with symmetry? Right, get a little bit of extra practice. Or when you're doing your homework, try to do each one both ways and make sure you get the same answer. Again, on an exam, don't do that. To get the answer, you only need to do it one of the two ways, but for practice, it's good practice to do it both ways and to be comfortable with both approaches. Just again, so you have more tools in your toolbox. And when you come up on a problem, you have a couple different choices. But also, as I mentioned last time, if you're getting confused with the two different methods, maybe stick with complementary events first. Stick with that one first, get that one down solidly, and then move on to symmetry. That might be the approach that I would take, I think. Okay, let's look at probability z bigger than 2. So again, I will draw out a picture. So here's 0. This inflection point is at 1. And 2 is going to be a bit further out than that. Probability Z bigger than 2 actually is not that big of an area. It's actually hard for me to color it in and even make it show up. It's sitting right there. This should be less than 50%, and actually by quite a bit. It should be a lot less than 50%. So I'll write 2 less thans just to remind myself. I'm expecting a number not like 40%, but like a few percent, 2%, 5%, something like that. This is Z. Let's use symmetry for this one. I'll remind myself that Z is symmetric about 0. I have a right tail area. I need to somehow convert it to a left tail area to use my table, or to use Excel for that matter. So when I flip about 0, the black curve looks the same. The standard normal is symmetric about 0, so its PDF looks the same. The +1 over here kind of comes to a -1, and the +2 comes to over to a -2. And now I'm looking for this area. And this is still Z. Or in other words, probability Z is bigger than 2 is equal to the probability Z is less than, changing the inequality sign, because we have a left tail area now, -2. The index became the opposite because I flipped everything above 0. Positive become negative and vice versa. But probability Z less than -2 is a left tail area, which means I can just use my table to look up that probability. Now my positive Z-scores picture doesn't mesh with the second picture over here. This is a negative Z-score. I know I'm expecting the area to be much less than 50%, so I'm on the wrong side of the table. This side of the table, the negative Z-score side, meshes much better with all of that. And I'm looking for the area to the left of -2.0. So looking in this row, and 0/100ths, looking in this column. And that should be 0.0228. Or 2.28%. And that is what I expected. Something that's a lot less than 50%, a couple percent. That's what I expected. I can visually see that this area has got to be quite small. This probability has got to be quite small. So I do take a little bit of care to try to get my normal distribution pretty nice looking. I'm not going for perfection, but I do want it nice enough looking that I can kind of estimate whether something's going to be a really small area, like a moderate area less than 50%, pretty close to 50%, moderately above 50%, or a really big area, right? That's going to kind of help me, just help me error check. If I were to grab a wrong number from this table, I don't know if I used -0.2 for some reason instead of -2.0, I get 42%. Well, 42%, I mean, okay, it is less than 50%, but this blue area here certainly doesn't look like it's 40% or so of the whole area. Okay. Then let's look at probability Z bigger than 1.735. So I have my standard normal, my inflection point at Z equals 1, going another one of those distances out as Z equals 2, and 1.735 is in between those two. I'm looking for the area to the right of that, and again, this should be a lot less than 50%. So maybe something in the ballpark of 5%. not something like 40%. Now here, maybe I'll use my complementary events rule just to show the other method at work. This is a right tail area, which does not match with the information given by my table or by Excel. It's not just an issue of me using the table. I'd have to do the same thing if I was using Excel. So to construct this area, I could take the entire area under the curve, which includes the area to the right of 1.735, which I want, but also includes a whole bunch of area to the left, which I don't want. So to get rid of that area to the left, I just subtract it off. So here's my 1.735, and I'm taking off the area to the left of 1.735. And these are still z, this is still 0. Or in other words, probability z bigger than 1.735 equals the whole area under the curve is 1 minus probability z less than 1.735. And I'm going to choose to use 1.74. I'm going to round to 1.74 to the hundredths place because that's what my table requires. So what's probability z less than 1.74? That's a positive z-score. Let me jump over to the positive z-score side. And I'm looking for 1.700 to the 10th place, and then 4 hundredths. And I see I get 0.9591. And again, I might be tempted to grab 0.9591 and think that's my answer, but remember, my answer should be a very small number. This is 1 minus 0.9591 for the answer. Don't forget about that 1. And that's 0.0409 or 4.09%. And that is a number a lot less than 50%. On the order of a few percentage points, that's what I expected. Any questions on using this normal table so far? So probability z less than number. Pretty straightforward application of the table. Probability z bigger than number. We have a right tail area. We need to flip it around in some way to a left tail area, either directly by using symmetry or kind of indirectly by using complementary events. So those were 2 of the 3 intervals that we said were kind of typically interesting intervals for us to talk about, or interesting events for us to talk about in continuous distributions. There was a third event that was, it was a candidate for an interesting event, and that was the probability that our random variables between 2 numbers. Right, so the person's height is between, say, 5'11" and 6'1", something like that. Or what's the probability that z is between -1 and +1? Now we might actually remember back to our empirical normal rule. Our empirical normal rule, remember, said, this was near the end of chapter 3, said, well, if a data set is approximately normally distributed, which of course an actually normally distributed random variable is certainly meets that criterion, then the probability that we're within 1 standard deviation of the mean, remember the mean for z is 0 and the standard deviation is 1, so this is really saying within 1 standard deviation of the mean, we said that should be about 68%. We gave no argument for where that came from, and I said we would, later in the course, substantiate that. And here we are later in the course, and we will substantiate it. And as an aside, I'll leave as an exercise that this should be about 95% and that this should be about 99.7% within 2 or 3 standard deviations of the mean. So as an exercise, you can check these. We'll check the 68% within 1 standard deviation of the mean. So what do I have here? I have my z distribution centered at 0. I'm interested in z indexes -1 and 1. They're going to be important. And I'm looking for the area between those 2 indices. I'm looking for that area. Note that there's no area in the tail out here, and there's also no area in the tail out here. No area in the left or right tail. Just to make that clear. I know some of these are probably showing up kind of small on your screen, especially if you're on a smaller device, but we just have area between -1 and 1 that we're concerned with. If I try to use symmetry here, I get exactly the same thing back. So that's maybe not going to be super helpful. But I can use something like the complementary event rule. Not exactly complementary events. I could really force the issue and use exactly complementary events and then symmetry to get the answer, but that's kind of there's a much better way to do this. I have an area between 2 numbers. My table gives me areas to the left of numbers. So one way that I could think about constructing this area between -1 and 1 from areas to the left, I could start with the area to the left of 1. The area to the left of 1 includes all the area that I want. Here is -1. It includes all of this area that I want, that I'm interested in, but it also includes some extra area to the left of -1 that I don't want included. So I take the area to the left of 1, which includes some area I do want and some area that I want to get rid of, and then I subtract off the area that I want to get rid of. What area do I want to get rid of? That area to the left of -1. Or in other words, I see that probability z is between -1 and +1 is the probability z is less than +1. I don't know why I keep wanting to write -1 for +1. The probability z less than +1, that's what I have here, the area to the left of 1, which again includes all of the area that I want, but also some extra area that I don't want. So I subtract off the area that I don't want, that area to the left of -1. Now, again, it's really easy to make a mistake here if you're not drawing out the pictures and do something like probability z less than 1. I mean, let me erase this bit here. Probability z less than 1 kind of looks reasonable because it looks like that. But then it's really easy to do something like minus probability z bigger than -1 if you just look at that inequality there and just kind of plop that in the other probability. But remember, what we're doing is we're getting rid of the area that we don't want here. So we're subtracting our probability z less than -1, in a sense, the complementary event. It's really hard to think through this, at least I think it is, if you don't write out the pictures. But if you write out the pictures, it's just like, cutting out pieces of paper or something. It's much more intuitive. Okay, so what's the area to the left of +1? Well, that's a positive z-score. The area to the left of +1.00 is 0.8413. And what's the area to the left of -1 that I have to get rid of? to get rid of that area. I look down my z-index column for negative 1.0 and negative 1.00. Area to the left of that is 0.1587. And let's bring our calculator up. And what do I need? 0.8413 minus 0.1587. So 0.6826. And that meshes with our 68% part of the empirical normal rule. So that is the confirmation of this empirical normal rule claim up here. And as I said, as an exercise, take a look at 2 and 3 standard deviations and see if you get something close to 95% and 99.7% for those two. Now, as a little aside, I do want to kind of demonstrate something over here. That if we were looking for the area between -1 and 1, I could actually consider the complementary event. I could construct this as the whole area so the area under the whole distribution minus, what do I have to take away to be left with just the area between -1 and 1? Well, I actually have two little pieces I need to take away. I need to take away the area to the left of -1 and also the area to the right of +1. So I can say probability -1 less than z less than 1 is 1 minus the probability that what? Z less than -1 or z bigger than +1. Clearly, these are mutually exclusive. So this is 1 minus probability z less than -1 plus probability z bigger than +1. And I also note that these two have to be the same area by symmetry. Right, if I looked at the area to the left of -1 and flipped it over the zero axis, the -1 become +1, the left area become a right area, or vice versa. I could do the same to the right area, flip it over, make it look like the left. This is actually 1 minus, say, twice the probability z less than -1. So I could use, sorry, my allergies are bothering me today. I could use complementary events. Sorry. I could use complementary events in this step and then use symmetry here. And what's probability z less than -1? We actually found that over here. That was 0.1587. And that's exactly our same 0.6826. This is going to be a helpful way to think about things when we move into chapters 7 and 8 sometimes. But again, this is a little bit more advanced. But I want to kind of show you this as a little bit of a, just a sneak preview of some of the stuff from chapter 7 and 8. And really, if we look at this 0.8413 from the bit over here, this is like 1 minus 0.1587. So we have 1 minus one of the 0.1587s, then minus another one, right? This 0.8413 just kind of got rid of this tail first, and then separately we got rid of that tail. And here we just kind of, in some sense, kind of did both at once. Oh. I think I need to restart my computer. It's been like not wanting to select things whenever I soft click on the touchpad. I updated something with Windows the other day because it was not letting me start up any of my like Outlook or anything. It all of a sudden just stopped working. So I updated some stuff and installed some stuff, and now it's been acting a little wonky. I think I have to restart it again. I wish humans worked that way. Like if I was sick or something and not feeling well, I could just like go to sleep for 20 minutes and wake up and then just be perfect again. Uh, Not so lucky though, I suppose. Okay, so let's look at something that's a little more irregular. This had a nice symmetry to it. And by the way, the nice symmetry of the interval here, that meshed with the symmetry of the distribution, symmetry about 0, is really what led to this method over here. So this method of using complementary events and then symmetry is kind of a special case, right? This would be the more general way to do it, which is why I stress doing it this way. So let's look at this probability. Probability Z is between negative 0.35 and 1.24. Here's 0. Here's 1 and 2 and negative 1. So just labeling 0 at the peak, those two inflection points, and then using the 0 to 1 distance to approximate the 1 to 2 distance. I have two Z indices I'm interested in, negative 0.35 and 1.24. And I'm looking for the area between those. And it's actually quite difficult for me to get an idea of how big this area is. It's really hard for me to even say if it's bigger than or less than 50%. I don't have the entire right tail. If I did, then I could say, okay, it's the whole right side plus a little bit bigger than 50%, but I don't have that whole right tail, right? And I'm not strictly to the right of 0, in which case I could say that it's less than 50%. If I was missing some of the area between 0 and a positive number and also missing some of the right tail, that goes in kind of the same direction. But missing the right tail means, say if I started with an area like 0 out to infinity, missing the right tail means I go down a little bit in area, but then I go up a little bit in area, picking up this little slice over here. So I don't know how those two balance. If I really wanted to force the issue, I recommend maybe doing this once or twice just to kind of wrap your head around it. But I don't recommend doing this on every prop. I just think it's too much work for the value that it provides. If I really wanted to force the issue, I could actually come off to the side here and look at my empirical normal rule and investigate what it really kind of says about these normal distributions. What can I infer from the empirical normal rule? So here's 0, here's 1, and negative 1, 2, and negative 2. Now, one thing I know from the empirical normal rule is the area between negative 1 and 1 is about 68%. But I also know that this is a symmetric region. the area from 0 to 1 should be the same as the area from 0 to -1. This should be about 34 and 34%. I'm not going to write the percentage signs because it's a bit crowded already. Okay, that wasn't too bad. But now I can look at -2 to 2. I know that this should be 95% area from -2 to 2. 68% is already accounted for. So what is 95 minus 68%? So that's 27 percentage points. Let's call it like 28-ish. That's the area combined between these two areas. From 1 to 2 and from -1 to -2, those two areas put together should be about 27%. Or these should be something like 13 or 14. 13, maybe I'll just say 14. So this gives me 68, 78, 88. That brings me up to 96 total. Now I have 96 total percentage points accounted for. I have 4 percentage points unaccounted for. So this left tail to the left of -2 should be like 2-ish%. And to the right of +2 should be like 2-ish%. So how does this help me over here? Well, I know that I've got a full 34%. Here I'm adding something positive, but less than 14%. So this is between 0 and 14. And here I'm adding something between 0 and 34%. So on the high end, I have 34 plus 34 plus 14. So 68 plus 14, that's like 82%. And on the low end, I basically have 34%. Right. So that's my estimate. This answer has to be between 34% and 82%. More or less. I mean, if I got 80, 2.1 or something percent, I did round these numbers, of course. So, but it has to be essentially between 34 and 82%. Even if I got 85 or 86%, I would think that I've done something wrong. Or same if I got 30% or even 31%, I'd probably think I did something wrong. I don't think it's going to round that much. So practically speaking, how would I use this? Probably I would look at this and I would see, okay, I have a whole 34%. This sliver is not that big. And this sliver also, I don't think is that big. Probably a little more than 34%. Maybe somewhere in the ballpark of 50% would be my guess. Right? So typically I wouldn't go this far. Typically I'd say, okay, got to be bigger than 34%, not a ton bigger, probably around 50%. And now I have a ballpark for where I'm looking for my answer that I can check my answer against. And if I make any, really serious errors, I'm likely to catch them. Give me 1 second before we start working on the details here. Okay, so let's work through the details then. So again, I have this area from -0.35 to 1.24. I have more or less hard bounds on what this answer has to be, and also kind of a soft estimate, probably in the ballpark of 50% or so. I can construct this area I don't want to take the area under the whole curve to start with. I might as well leave off that right tail and just take the area to the left of 1.24. The area to the left of 1.24 is a left tail area, and I'll be able to find it using my table. Now, again, that includes area that I want, negative 0.35 over here. It includes area that I want between negative 0.35 and 1.24, but it also includes a bunch of area that I don't want. So I get rid of the area that I don't want by subtracting it off. Or we have the probability negative 0.35 less than z less than 1.24. We can rewrite that as the probability z less than 1.24. This accounts for all of the area to the left of 1.24, including the stuff we do want and a bunch of stuff we don't want. So we subtract off the area to the left of negative 0.35, the stuff we don't want. This is also a left tail area, which I can also find from the table. Probability z less than 1.24. I don't want the negative z-score side. I want the positive z-score side of the table. I look for 1.2 in my column here, and that indicates this row. So I'm looking for an answer somewhere in this row, and I'm looking for the answer corresponding to 4/100ths. And that intersection is right here at 0.8925. And now I need the area to the left of negative 0.35. That's on my negative z-score side. And it's all the way down here at the bottom. I'm going to have to kind of count across. Here's negative 0.3, that row. 0.30, 1, 2, 3, 4, 5. So just counting across my hundredths, I get 0.3632. And I bring up my calculator, do the subtraction. And that gives me 0.5293, 52.93%. That does mesh with my hard limits here, 34 to 82%. And it also meshes with my kind of soft guess. 50-ish% is what it kind of seemed like. 34% plus a little bit, but not a trivial bit, right? So 52%, 53% does seem to mesh with that. Any questions on this? Any thoughts on any of this material so far? So pieces of advice, always draw the pictures, even on simpler problems. When you feel like you've got it down, still draw the pictures. It takes 15, 20, 30 seconds or something like that to draw a picture. And it really is helpful for keeping things straight, making sure that everything is pointed in the correct direction, making sure that you get your signs and both your plus minus signs and your inequality signs kind of pointed the right way. So always draw the picture. And this is something that as you drill it, as you go through more and more problems, jumping back and forth between the picture and the algebra and the information in the table becomes a lot more fluid. At first, it's kind of like, what does this table even mean? Wait, which are these the indices or are these the indices? But the more that you use the table, the more that you work with constructing left tail areas from different shapes, the more you get used to it, right? You might mistakenly, construct right tail areas from this shape and say, oh, wait, I can't actually use my table, at least not very easily, not with using extra steps and symmetry and so on. I can't easily use my table to find those. uh, let me erase that work and go back and make left tail areas. So, if you take a misstep here or there, that's what practice is for. And, after 10 or 20 problems, things become much more fluid. Okay, so now we're going to move into looking at inverse problems. So the normal distribution problems we did before are very nice for, like, I have a distribution that I know is normally distributed, and I want to ask something about the likelihood of some event occurring. These inverse problems, kind of at first glance, it seems like the problems are almost artificial. Why would we ever want to do this? But it actually turns out that these inverse problems, after we get out of chapter 6, in chapter 7 certainly, and also in, say half or so of chapter 8, half of the points of interest in chapter 8, we'll actually be dealing with these inverse problems. So these are actually at least as important as the material we've just covered. Okay, so let's look at a few of these. So what is an inverse problem? What did we do up here? What we did up here is we were given indices and we were asked to find areas, right? That's what we've done this whole time. It took on different shapes and different forms, but we were given an index, asked to find an area, right? Given an index, asked to find an area. So if we're given an index and asked to find an area, or if we're given the information for the index row and column and asked to find the number in the field of the table, the probability of the area, that's kind of a forward problem. An inverse problem goes the other way. Essentially, I'm asking you to find a number in the middle of the table and determine which row and column that probability or area is associated with. In this case, maybe 2.54, negative 2.54. So here I'm given an area and asked to find an index. So graphically, I'm asking to find a z-index called k, such that probability z less than k, such that the area to the left of k is, well, in this case, 5%. So I'm asking you to find k with 5% area to the left. I know the k has got to be less than 0. Maybe I'll write it below k. I know k has got to be less than 0 because if k was 0, the area to the left would be 50%. That's too much. I need to have less area to the left, so k has got to be less than 0. So k has got to be negative. What is k actually? It's actually just the 5th percentile of the distribution, right? It's the z number that separates the bottom 5% of the distribution from the top 95%. It's just the 5th percentile. So we label it the same way that we label percentiles. We label it p sub 5. P sub 5, or the 5th percentile. It's the z-index with 5% of the distribution to the left, 95% to the right. We call that the 5th percentile. How do I figure out what this number is? I know k is going to be negative. Is it -1? Is it -2? Is it negative 1.35? Well, I'm looking for an index that has area to the left of 5%. So really what I'm looking for is in the field of my table, somewhere in here, I'm looking for 0.05 or thereabouts. the same way that I had to round my indices to the nearest hundredth so that they would mesh with these indices on the table, I have to accept a little bit of approximation here as well. So I'm looking for the probability from my table in this field that's closest to 5%, to 0.05. So I have numbers like 0.0427 or 0.0594 that are getting close. And actually, if I look right here, I see 0.0505 and 0.0495. They actually straddle 0.05. This is a special case. We see there's an asterisk there, and we follow that down below, and we see that for a z-score of, I'll blow this up, for a z-score of negative 1.645, the area to the left is 0.0500. Now, as a side note, that's not exactly 5%. If you went another couple of decimal places down the line, and you're going to get some stuff that's not zero, but it's quite close. And because we're actually quite often interested in the 5th percentile or the 95th percentile, we kind of pull this out as a special case. So what should K be? Negative 1.645. In other words, the area to the left of negative 1.645 on a standard normal is quite close to 5%. We could also look at, for example, probability z less than k equals, I want to make sure I'm not redoing any of these, say 0.25. What's the 25th percentile? We would call this P25, the 25th percentile. We might call it Q1, but I think that's maybe a little less common in distributions like this. So again, I have z here. There's 0. I'm looking for an area to the left of 0.25. If k was 0, the area to the left would be 50%. That's way too much. I know that k has got to be less than 0. I'm looking for an area to the left of 25%. I know that k is going to be a negative index, so I'm on my negative z-score side of the table. And I'm searching for, let me try to zoom this out just a bit. What did I do here? There we go. I think 105 is what has been working pretty well. There we go. So on my negative z-score side of the table, and I'm looking in the middle here where my probabilities, where my areas are, I'm looking for one that's pretty close to 0.2500. So I look down here and I see, okay, and I see 0.2514 and 0.2483. Well, 0.2514 is 14 10,000ths above. 0.2483 is 17 10,000ths below. I'll take the one that's a bit closer at 14 10,000ths away, 0.2514. That's the closer one to 0.2500. And I notice that that is in the row corresponding to negative 0.6 and the column corresponding to 0.07. So that's going to be negative 0.67. So a z-index of negative 0.67 is at the 25th percentile. It has 25% area to the left. Or probability z is less than negative 0.67 is approximately 25%. And we could do something similar with a right tail area. We could ask the question, probability z bigger than m equals 0.35 for what value of m? In other words, I draw out the picture. It looks like this. Here's z. And I'm looking for a z index m. I'm looking for a location on the horizontal axis m with 0.35 area to the right. Well, again, if m was 0, that would have 50% area to the right. That's too much. M has to be positive so that its area to the right is less than 50% or exactly 35%. So I see that m has to be bigger than 0. And I'm looking for an area to the right of m of 35%. What should m be? Well, there's two ways for me to approach this. Just like before, I need to flip a right tail area to a left tail area. I can use symmetry. I can flip everything about the 0 axis. So m, be careful, m gets flipped to negative m on the left side of 0. The area to the right gets flipped to an area to the left, but it's still 35%. Its size is still the same. It's just in a different location. But wait, this is just the kind of thing we just solved. It's like the 35th percentile. So negative m is the 35th percentile. It's P35. Let me come over to my table here and look up in the middle of my table, looking for a number as close as I can find to 0.35. So I see, oh, I see these two, 0.3520, 0.3483. 0.3520 is 20 10,000ths away from 0.3500. 0.3483 is 17 10,000ths away. I don't know why we constantly have to have things popping up but on everything these days, but uh, I guess I'm an old get off my lawn guy by this point. But we see that 0.3483 is just a bit closer. And that corresponds to a z index of negative 0.3. And then we were in the last column, so 9. So negative 0.39, and be careful. Remember, m was positive. Negative 0.39 is what negative m is. M must be 0.39. And remember, this is a z index. It's a location on the horizontal axis. Even though it's a number between 0 and 1, it could look like a probability if we weren't keeping the context in mind. It is a z index. It's a location on the horizontal axis. It's not an area or a probability. So 0.39. Or the other way we could do it is we could use complementary events. So I'm looking for m with an area to the right of 0.35, 35%. And I can actually, I think I can pretty readily see that an area to the right of 35%, well, that's got to just correspond to an area to the left of 65%. Right? In other words, probability C bigger than M equals 35% has got to mean that probability Z less than M is 65%. So in other words, M with area 35% to the right, M has got to be P65, the 65th percentile. Remember, negative M was the one that was P35 in the last thing. M itself is the 65th percentile. I know that M is positive. I'm going to look on the positive Z-score side of the table. I'm going to look in the field here for something pretty close to 0.6500. And I find it here, 0.6480 to 0.6517. Those two straddle 0.6500. 6480 is 20 ten thousandths away. 6517 is 17 ten thousandths away. So I'm going to go with 6517. And that is in the row 0.3, in the column 0.09. So again, that's positive 0.39. Now the notation we have for this, for Z, is that we would say Z subscript 0.35 equals this number, 0.39, this Z index. So I'm sorry I didn't make the notation. You know, we have, when we're dealing with percentiles, we call a P subscript percentile like P5, not P.05. When we're dealing with left areas or percentiles, we denote them this way. The 5th percentile is P5, the 10th percentile is P subscript 10. When we're dealing with right areas, this Z index, sometimes called a critical number, is Z subscript, for the say the 35% area to the right is Z subscript 0.35. You can put a 0 in there. It's especially nice to put in there whenever you're writing it by hand, but I usually don't write it in there when I'm typing it, because it just seems to get a little too cluttered when you put the 0 in there. But Z subscript 0.35 is what we call this Z index with 35% area to the right. I don't know why it's not Z subscript 35, but you know, somebody decided it would be this way, and that's the way that it is. Okay, and then let's look at an example like this. I have a lower bound and an upper bound, and I want 95% between them. Now, if I just said I want you to find a lower and an upper bound with 95% area between them, this would be an ill-posed problem. You could pick a lower bound way off to the left, and the upper bound would be some number, or your lower bound could be a little less to the left, and your upper bound would be a different number. There's lots of lower and upper bound combinations that'll give 95% between them. But note that we're not just asking for any lower and upper bound, we're asking for a symmetric lower and upper bound, negative n to positive n, and we want 95% in here. Now here, if I kind of imagine n starting very close to 0, so a very small interval around 0, the area between negative n and positive n is close to 0. As I increase n, so this might be a graph of like n versus the probability from negative n to n. When n is 0, probability is 0. As I start increasing n, my interval gets wider and wider, and I start accumulating probability, something like that. Now this should be well posed. It should be that as I keep increasing n, my probability keeps increasing. So this should be a one-to-one function, and there should be exactly one n where that input gives me an output of 95%. So this seems to be a well-posed problem, and indeed it is. Because I'm imposing symmetry here, if I just said I want some lower bound and some other upper bound that aren't inherently related to one another with 95% in between, then I have lots of different choices. But I should be good here. Now, there's a couple of different ways I can approach this problem. But both ways make use of my knowledge about the normal distribution. This is Z. So I want 95% area from negative n to n. Negative n to n is also a symmetric interval around 0, and my normal distribution is symmetric about 0. By complementary events, I know that the combination of these two tail areas to the left of negative n and to the right of positive n has to make up the remaining 5%. In between negative n to n is 95%, so the rest combined between these two tails has to be 5%. But these tails also have to be the same size as one another, because to the left of negative n and to the right of positive n, those are symmetric areas. They have to be the same size area. So that actually tells me that each one of these has to be 2.5% area. So I have a couple approaches now. I could say that n is like something that has an area to the left of 97.5%. Well, that would be the 97.5 percentile. Or I could see that maybe negative n is the 2.5 percentile. Figure out what the 2.5 percentile is, and then just take the negative off of it to get n. Or maybe I even see that n is z 0.025. So I have a few different ways to approach it. I think probably the most natural is the first way that I wrote down. Right. I don't have to remember the extra step of taking off the negative at the end. When I look up 2.5% area on the Z table, it's going to be on the negative side. I'm going to get negative something out of it. And then I'm going to have to remember to take the negative away. It's an easy little step to forget at the very end. If I look at this as n equals z 0.025, my table doesn't naturally give me areas to the right, so then I got to do more work to convert those to areas to the left. I think it's easiest to just think of this as the 97.5 percentile, at least at this stage of the game. In the future, when we get to chapter 7, we'll actually often think of it this way, especially when we have a slightly different table that is kind of rephrased in these kind of terms and areas to the right terms, then it'll be very natural for us to think of it this way. But for right now, we're going to think of n as the 97.5 percentile. So I'm going to come over here to my, and of course, n is positive. So I'm going to come over here to my positive z-scores side of my table. And I'm looking for an area to the left of 97.5%. I'm looking for an area in here that's close to 0.9750. And I have it right here. And this time it's actually smack on, just by chance, 0.9750. Right on the nose. I don't have to pick between which of the two things is closest. It's right on. And that's associated with the z-index in row 1.9 and in column 0.06. So that's 1.96. So what should n be? N should be 1.96, or in other words, the area under Z between negative 1.96 and positive 1.96 is pretty darn close to 95%. Okay, probability that negative 1.996 less than Z less than positive 1.96 is approximately 95%. Any questions on this? I know we've taken quite a bit of time, maybe 1.5 lectures at this point on just this part of section 6.1, dealing with standard normal distributions, how we look up probabilities and indices, how it associates with the table, how we convert right tails or middle areas to areas with left tails. We spent quite a bit of time on this, but I think this is such important material that I always do spend a lot of time on it. Like I mentioned, I think before that, roughly speaking, just about every problem from this point on in the course is at some point going to involve looking up something to do with probabilities or indices related to a normal distribution, or at least close variants thereof. We might use a slightly different distribution, or we might use a slightly different table, but this general idea is really foundational material for the rest of the course. So if I haven't harped on it enough already, drill this material, make sure that you're comfortable with, I would say both the symmetry approach and the complementary events approach. If you want more practice, you can always, if you go through the homework and you feel like you stumble through it a little bit, you can always go back and reload problems. It should reload it with new numbers. I mean, the problem stem will be the same, but the numbers should change from from attempt to attempt. There's like a practice another version, I think is what the button says. Or you can always go to the book, practice problems right out of the book, things like that. So yeah, I strongly recommend going through this part of section 6.1 in the near future, over the next few days, taking the time to drill these problems to really achieve mastery in this area. We're not going to start general normal distributions today. We only have 10 minutes left. But when we get to general normal distributions, we're going to see that the way that we solve similar questions about general normal distributions when the mean and standard deviation is not 1 is we reframe them as questions about standard normal, answer them in standard normal, and convert the answer to general normal. So this is foundational material for this next section, for the rest of chapter 6, and definitely for chapter 7 and 8 as well. So, the more challenging material in the course has this at its foundation. If you really master this material, you're really setting yourself up for success for most of the rest of the course. If you struggle with this material and don't put in the time to master it, the rest of the course is going to be quite challenging. So we'll end a few minutes early today, but take this extra few minutes, maybe work through a couple of problems, maybe even go back through some of these notes, like we solved some of like this problem with symmetry. Go back and do it with complementary events. Do you get the same answer? We did this one with a complementary event. Can you do it with symmetry and get the same answer? Right. So go back through, practice these techniques. And I think that's all that I have to say for today. So I'll end the recording.